Everything is made from atoms. Cheese, handbags, the Eiffel Tower, you name it. And atoms are very, very, very small. But it doesn't stop there. The atom is made up of even smaller particles called subatomic particles. Welcome to the weird world of atomic structure. The centre of an atom contains protons and neutrons, while electrons are arranged around the nucleus in energy levels or shells. The energy levels are usually drawn as circles around the nucleus. Both protons and electrons have an electrical charge of the same size. Protons are positively charged and electrons negative, while neutrons are, you guessed it, neutral. Like Switzerland, but smaller. The number of electrons is always matched by the number of protons in an atom. I'll see your 4 electrons and I'll raise you, no I won't, I'll just match your 4 protons. This means atoms have no overall charge. The number of protons in an atom is called an atomic number. So if an atom has 4 protons, that's its atomic number. Atoms are arranged in the periodic table in order of increasing atomic number. At number 1, hydrogen. At 2, helium. At 3, lithium. At 20, calcium. At 57, something else. Electrons can only exist at clearly defined energy levels. Thankfully, you only need to know about the first 4 levels for GCSE. Yeah, not quite there yet. We need to talk about energy levels. An atom's energy levels, also known as electron shells, are filled starting with the innermost one, closest to the nucleus. A level needs to be totally filled before moving on to a higher level further out. The first shell, with the lowest energy level, can contain a maximum of 2 electrons. Levels 2 and 3 a maximum of 8 electrons each, and level 4 a maximum of 18 electrons. The electronic structure of an atom can be shown as a diagram or using numbers. You need to know both for all these little beauties. So let's use what we know to build a model of the atom lithium. This has the atomic number 3, so it must have 3 electrons. That means 2 at a lowest energy level, the innermost shell, and 1 in the second level. Whereas a carbon atom, with atomic number 6, has 2 electrons in the lowest energy level and 4 in the next level. Heavier construction work this. In the exam, you'll also need to be able to write down the electronic structure of an atom. Let's take lithium again. This is written as the chemical symbol Li, followed by the number of electrons in each energy level, in this case 2, 1. The periodic table is arranged so that every time we fill an energy level, we start a new row or period. You can see that the number of occupied energy levels is the same as the period number. And as you go across each period from left to right, an energy level gradually becomes filled with electrons. 1 electron on the left to maximum on the right. What a system! The number of electrons in the highest energy level matches the group number, with the exception of group 0, which has 8 electrons. Oh, and apart from helium, which has only 2. And they call this a system? Ah, I see it means that the highest energy level is full. Okay, so exceptions to the rules aside, let's use what we know to create a diagram for sulfur. Looking at the periodic table, it has atomic number 16. Ah, here it is in the third row of the table. So it has 3 occupied energy levels. It's in group 6, so it has 6 electrons in the highest occupied energy level. We now fill in the empty rings with the appropriate number of electrons. 2 for the inner ring, 8 for the second ring. Last job is to check that the number of electrons matches the atomic number. Well, it's not really a job, is it? More like a walk in the park. So now you know about atomic structure. It's easy when you know how.
An atom becomes an ion by losing or gaining electrons. This isn't like when I lose stuff. They do this deliberately to achieve a full highest energy level, with no gaps or no spare electrons hanging around. This leaves the electron structure the same as that of a noble gas. Classy. For metals, the simplest route to a full highest energy level is to get rid of the few spare electrons they have on the outside. Goodbye atom, hello ion. For non-metals, on the other hand, the best route is to take on more electrons to fill the gaps in their highest energy level. In atoms, there are equal numbers of protons and electrons, but in ions there is now an imbalance. This gives them an overall electric charge. Some are negative, others are positive. Metal atoms such as sodium and aluminium lose electrons and become positively charged ions. Non-metal atoms like chlorine and oxygen gain extra electrons and become negatively charged ions. Let's look at some examples. First, let's look at metal ions. Sodium has 2 electrons in the innermost energy level, then 8, and finally 1 in the highest energy level. To become a sodium ion, it loses the electron from its highest energy level. Ruthless. You see? Metal ions. Nerves of steel. The diagram of a sodium ion is very similar to neon, but they are not the same thing. Remember, neon has only 10 protons in the nucleus, whereas sodium still has the original 11. Always check the nucleus. 11 protons versus 10 electrons. The extra proton gives the sodium ion an overall 1 positive charge. Sodium 1, neon 0. Now, magnesium is another metal, but this time with 2 electrons in its highest energy level. To become a magnesium ion, it has to lose both of these. Rules is rules. We use a 2+ to show this. That might sound contradictory, but with 2 negatively charged electrons gone, that gives the magnesium ion a 2+ charge overall. Because metal atoms lose electrons from their highest energy level, the number of charges on a metal ion is the same as the periodic table group number for that metal. No way! That is so spooky. Check this out, I am freaked. Non-metal ions gain electrons. Take fluorine, for example, in group 7. It has 7 electrons in its highest energy level. It takes 8 electrons to fill that energy level, so it needs to gain 1 more to become a fluoride ion. Well, if that's what it takes to get toothpaste. Again, looking at the diagram of the fluoride ion, it is remarkably similar to neon, but neon has 10 protons and the fluoride ion just 9. It's important not to get the two confused. 10 negative electrons and 9 positive protons leaves fluoride with a net result of 1 negative charge. We write a minus sign to show this. Oxygen, in group 6, is another non-metal, 6 electrons in the highest energy level. So to make it up to 8, an oxygen atom is going to gain 2 electrons to become an oxide ion. The position of the non-metals in the periodic table tells you how many electrons they need to fill their highest energy level, which tells you the charge on the ion. So where do the electrons come from or go to? It actually works out at a fair exchange. The electrons leave the metals and join the non-metals. They're all happier that way. Truth is, it's all about bonding. The positively charged metal ions and the negatively charged non-metal ions strongly attract each other. For example, sodium bonds with chlorine to form sodium chloride. Magnesium bonds with oxygen to form magnesium oxide. There is a strong electrostatic force of attraction between these oppositely charged ions. This is called an ionic bond. One of the things you will need to be able to do is draw a dot and cross diagram to show the ions in some common ionic compounds. Take sodium chloride, for example. Draw the metal ion, in this case sodium, using dots for the electrons. Draw the non-metal ion, chloride, using crosses. The electron that is transferred to the non-metal is shown as a dot, indicating clearly that it has come from the metal atom. Where there is more than one shared electron, make sure to use all the electrons. Here is magnesium oxide, for example. Sometimes the chemical formula for a compound includes uneven numbers of atoms. Nothing's ever simple, is it? For example, calcium chloride is CaCl2. It has 1 calcium ion and 2 chloride ions. you need to show the correct number of ions. The chloride ions have 1 electron each from the calcium, which is how they bond. So that's all you need to know about ionic bonding. It's all about full energy levels, charges, and attractions.
The rate at which a chemical reaction takes place can be extremely fast or incredibly slow. In the next few minutes, we're going to look at the rate of chemical reactions. Chemical reactions not depicted in real time. An explosion is a very fast reaction, but you can get very slow reactions too, like the weathering of rocks. So how can we measure the rate of a reaction? We can measure the changes in amounts of the chemicals taking part in the reaction by measuring their mass or volume. Say you start off with 2 different chemicals, an acid and a metal. As a chemical reaction takes place, we can measure the amount of the original chemicals that are left, like how much acid or metal is left. Or we can measure how much of one of the new products has been made, like how much hydrogen has been given off. What we choose to measure depends on whichever is the easiest to do. Okay, fine. For a liquid or a solid, we measure the mass, using a balance. For a gas, it's easier to use a gas syringe to measure changes in volume. I have tried to measure the mass, but gases won't weigh much. The rate of a reaction is how quickly the reaction is taking place, so we need to measure the time all this takes too. For example, suppose we measure a reaction between an acid and a metal, and we find that 24 cubic centimetres of hydrogen gas is produced in 3 minutes. Then the mean rate is 8 cubic centimetres of hydrogen per minute. 24 divided by 3 equals 8. For a reaction to take place, the particles involved must bump into each other. But that's not enough. The collision must have enough energy to make the reaction happen. This amount of energy is called activation energy. There are several factors that affect the rate of a reaction. They all come down to how often collision takes place and how much energy those collisions have. Let's look at the 5 factors you need to know about: temperature, concentration, pressure, particle size, and catalysts. Can you remember all that? No pressure. A higher temperature means particles are moving quicker, and so more particles have the activation energy necessary for a chemical reaction. Much like Formula 1 cars, the particles collide more often and with more energy, so the rate of reaction increases. Now then, the next factor is concentration. If one of the reactant chemicals is in the solution, then the reaction rate will go up if its concentration is increased. There'll be more of the chemical in a smaller volume, so collisions are likely to take place more often. Or in this case, I simply get a sugar rush. Next, let's look at pressure. If one of the reactants is a gas, represented here by the X's in a bubble, then increasing the pressure means that there are more reactant particles in a given volume. Less space, more chance to get under each other's feet. As the pressure increases, so does the rate of reaction. It's a bit like locking all the Big Brother contestants in the bathroom.
Let me out of here.
Next on the list is particle size. If a solid reactant is broken into pieces, there's more surface area, so more particles are exposed to the other reactants. As a result, there's a greater chance of a collision, so the rate of reaction increases. Even better is grinding them up into a powder. That really speeds things up. Double espresso, please. The last factor you need to know about is less obvious. You can use a catalyst. A catalyst is a chemical that speeds up a reaction without being used up in the reaction. Catalysts do this by reducing the activation energy needed for a reaction to take place. Different reactions require different catalysts. For example, the reaction between nitrogen and hydrogen to make ammonia can be speeded up by having some iron in the mix. The iron is a catalyst. It helps. It speeds up the reaction, but isn't changed in the process. It doesn't get used up either. It gets things moving, but doesn't take part. The chemical equivalent of a cheerleader. By increasing the rate of a reaction, catalysts are important in industry because they reduce costs. More useful products can be made in a shorter time. The Haber process uses an iron catalyst to speed up the production of ammonia, which is used, for example, to make fertilisers for growing crops. So now you know about the rate of reactions. Remember, a reaction takes place when particles collide with enough energy at or above the activation energy. And how do we achieve this incredible energy? Remember, the rate of reaction increases in 5 possible ways. if temperature, concentration or pressure is increased, or if a solid is broken into smaller pieces, or if a catalyst is used.
Here is a 7. Remember that. It's important. Why? Here is a clue. pH. We measure the strength of acids and bases by their pH value. If we look down there to low pH, we're looking at the acids. And if we look up there to high pHs, we see the bases. Which is a pretty annoying name for something that's high up on the scale, but there you go. They're the bases. Our title is Acids, Bases and Salts. So what is a salt? To find out, we have to investigate acids and bases. So we know that 7 is the key pH. Below this we have acids. Above we have alkalis. But what else can we say about them? Acids turn blue litmus paper red. Strong acids turn universal indicator red too. And weak ones turn it orange or yellow. What can we say about bases? What are bases anyway? They're usually metal oxides or metal hydroxides. Not all bases dissolve in water. Copper oxide doesn't, for example, but sodium hydroxide does. When a base can dissolve in water, it is also called an alkali. Just like bases, the stronger the alkali, the higher the pH value. Right up to pH 14 for the strongest. They turn red litmus paper blue. They turn universal indicator blue or purple if they're strong, and blue-green if they're weak. Sitting on our magic line at pH 7 are neutral chemicals. They are not acids and they are not bases. They don't change the colour of litmus paper. But they do turn universal indicator green. Water, for example, is neutral. So is paraffin. In the exam, you need to know about the reactions acids have with bases, carbonates and reactive metals. In all 3 of these types of reaction, a salt is formed, and you need to be able to work out which salt this is. Yes, in chemistry there are many different compounds called salts. One of them is indeed sodium chloride, the kind you put on your chips. But more generally, a salt is created when an acid reacts with a base, carbonate or metal, and it's not a good idea to eat them. Let's have a look at each of these in turn. First up are acids and bases. Bases, remember, are typically metal oxides and metal hydroxides. The reaction between an acid and a base is called neutralization. It produces a salt and water. Next up are acids and carbonates. Forgotten what a carbonate is? Think chalk, limestone and marble. Remember now? Thought so. Okay, so what do we get when an acid combines with a carbonate? We get a salt, water and, you guessed it, carbon dioxide. The carbon dioxide causes bubbling during the reaction. Lime water turns cloudy white when carbon dioxide is bubbled through it. Last up are acids and reactive metals. In this reaction, a salt is formed and hydrogen gas, no water. Remember the test for hydrogen? It can be detected with the lightest splint and burns with a squeaky pop. Thank you. Unfortunately, it's not enough to know that a salt is formed in the reactions we've described because, quite honestly, a salt is formed for each one. You also need to know the name of the salt. A salt name has 2 parts. Part 1, a metal name from the base or the metal itself. Part 2, a name from the acid that was used. Let's look at an example. Sodium hydroxide and hydrochloric acid react together and make sodium chloride. Sodium is the metal in the base, and the chloride comes from the name of the acid. It's like double-barreled surnames. You credit both halves of the creative process. Sulfuric acid makes sulfates, and nitric acid makes nitrates. You can see where they get the names. If you're making a salt from an alkaline solution, formed when a base dissolves in water, remember? You can be very precise. Start with the alkali. Add the acid very slowly and use universal indicator to tell when you reach a neutral pH. The indicator goes green. That means all the alkali has reacted with the acid, and all you have now is salt and water. Now evaporate the water. The salt crystals left behind will be larger if you do this slowly. Now, what if your base isn't an alkali? Copper oxide, for example. It and the other transition metal oxides and hydroxides don't dissolve in water. So this time add the base to the acid. Keep adding until no more will dissolve and some is left over. We call this the excess. No more will react because all the acid has been used up. Now filter the mixture to remove the excess base. Now all you have is salt and water again. Evaporate the water to leave the salt behind.
How do we represent motion on a sheet of paper? Apart from writing on it, that is. A cartoonist might add some speed lines like this, but a scientist uses a graph. For the exam, you need to know about two types of graph: distance time graphs and velocity time graphs. First, let's look at distance time graphs. These graphs can be used to represent a journey, and we're nearly there yet. The vertical axis shows the distance travelled from the start point. The horizontal axis records the time. All we need now are the journey details. So here's me on my bike, and I set out from where I live. Might only have one door and a chimney, but it's home. And I'm on my way to visit my gran. I spend half an hour at my gran's eating cake, chocolate, mint imperials, cough sweets, and all those cake bars that are neither cake nor chocolate, but somewhere in between. My distance from home doesn't change during that time. Then I come home, experiencing quite an intense sugar crash, but not a bike crash, obviously. I'm just riding a lot more slowly. So what can we learn from a distance time graph? The slope of a graph tells us a great deal. If the line is horizontal, then no distance is travelled, so the object must be stationary. If the line of the graph is sloped but straight, then the object is moving at a steady speed. I came back from my gran's less quickly than I went there. With that much cake on board, you're going nowhere fast. The line sloped more gently when I moved more slowly. Now, on to the second type of graph you need to understand: velocity time graphs. Yes, those don't look like speed lines, do they? Let's just stick to the science. On a velocity time graph, the vertical axis is velocity and the horizontal axis is time. Now here I am taking Gran to the seaside. Spain, in fact. She likes the food. Here is my speedometer. Okay, it's not my speedometer. No way, it's my story. Let's say I'm the pilot. Take off. Our speed goes from 0 to takeoff speed pretty quickly. I'm quite a smooth operator when it comes to my job. We keep accelerating as we climb. Then, we're at a nice steady cruising speed. Autopilot on. I pop back and chat to Gran, but she's watching Kung Fu Panda. So I try and chat up the stewardess. Hey, ladies. Great takeoff again, yeah. Whatever. Now, there's no acceleration going on, and notice what's happened to the graph. It's a horizontal line, but we are certainly still moving. That's a big difference between velocity time graphs and distance time graphs. Horizontal lines mean different things on each one, and coming to land, we decelerate and come to a nice, gentle halt. Our velocity is 0 again. So what does a velocity time graph tell us? A horizontal line means there is no change in velocity. Be careful, it doesn't necessarily mean the object is at rest. If we have a sloping line, then we have a change in velocity. The object is accelerating or decelerating. The steeper the line, the greater the acceleration or deceleration. And another thing, in distance time graphs, if the line goes back to 0, it means we have returned to the starting point. But in a velocity time graph, returning to 0 just means we've stopped moving. We're certainly not back at home. Before we finish, you need to know a few facts about working out speeds and accelerations. Let's first recap some basics. You can work out speed if you know how far something has travelled in given time. For example, suppose a car travels down a road 300 metres long and it takes 20 seconds. Its speed is how many metres it's travelled each second. So its speed is 300 divided by 20. That's 15 metres per second. If the car covered the same distance in 30 seconds, it would be going more slowly, and in that case the speed would be 300 divided by 30, which is 10 metres per second. So speed is distance divided by time, as in metres per second or miles per hour. Acceleration is the change in velocity in a given time. For the exam, you only need to be able to calculate constant, steady accelerations. Okay, just pretend this is a steady hand. Suppose a car accelerates from a rather gentle 5 metres per second to a scarily fast 35 metres per second. And suppose this speed up takes only 10 seconds. Not only is this a pretty nifty car, the driver must be a mentalist. The change in velocity is from 5 to 35 metres per second. So an increase of 30 metres per second, which took 10 seconds to accomplish. So it's increased its speed by 3 metres per second for each of those 10 seconds. Or, to put it another way, the acceleration is 3 metres per second. Or, you can say, 3 metres per second squared. Energy, momentum, forces and work. And some other stuff that's on the floor now. But how do they all fit together? First of all, work. What is work? Good, honest work. But how do we measure it? Well, work and energy are measured in joules. Work comes from force and distance. Remember how? Of course you can. That man pushing a rock image is pretty unforgettable. Well, it works like this. Here's a block. I push it in this direction for 3 metres. I'm using a force of 100 newtons, as you can see, and I've travelled 3 metres. All we need to do is multiply the distance by the force. So 3 metres times 100 newtons equals 300 joules of work. When you move a force over a distance, then you have done work. Now on to energy. Kinetic energy, potential energy, elastic energy, heat energy. Energy can change. A fast-moving bike wheel will transform its kinetic energy into heat energy pretty quickly if you brake suddenly. Next, pork pies. You can use a grapefruit if you're on a diet, but there's no real reason to, as we're not going to eat it. The point is to lift an object off the floor and put it on a shelf. Why not? It takes some work to lift the pie against the force of gravity. This work gets transformed into gravitational potential energy. That's the energy that would be released if it fell. If it fell. Now, the pendulum. When it swings, 2 forms of energy are transformed back and forth between each other. But how do you know which? When you pull the ball on a pendulum out to the side, it moves up too. It is higher up, so it has gained gravitational potential energy. Remember the pie. Same principle, but less messy. Now we let the ball go. What happens to the energy? Well, as it falls, it loses height, so loses gravitational potential energy. But it starts moving faster and faster, so it gains kinetic energy. As it swings back up higher, it gains gravitational potential energy again. But also, as it swings up, it slows down and loses kinetic energy. Over and over, the energy is transformed back and forth, gravitational potential energy to kinetic energy. GPE, KE, GPE, KE, GPE, KE, GPE, KE, you get the picture. Each swing will be slightly less than the previous one, as some energy is transferred to the surroundings, mostly as heat, but not much heat. Kinetic energy isn't just for pendulums. Anything moving has kinetic energy. It's all about mass and speed. Kinetic energy equals half mass times velocity squared. Velocity, of course, is speed. Suppose a 1,000-kilogram car is travelling at 10 metres per second. That's 36 kilometres per hour, by the way. Go granny. The car's kinetic energy is given by half the mass times the speed in metres per second squared. So that's half times 1,000 times 10 times 10. So that's 50,000 joules or 50 kilojoules. It all makes so much sense. Now, momentum. What is it? Momentum is also about mass and velocity, but its formula is simpler. The momentum of an object is its mass times its velocity. The more mass you have, the more velocity you have, the more momentum you have. Now, if you lose that momentum quickly, you will feel a large force. Lose momentum more gradually, and you'll feel less force. There's another thing about momentum you need to know. When something explodes, its total momentum before is the same as its total momentum afterwards. And also in collisions and crashes. Let's look in more detail at the cannon Total momentum before the gun fires is 0. Nothing is moving. After it fires, the cannonball is moving forwards. That's momentum in a forwards direction. The cannonball has small mass and large velocity. Momentum in the backwards direction will cancel this out. The cannon recoils backwards. It has large mass but small velocity. The two objects, cannon and cannonball, have equal momentum in opposite directions. They cancel out. That keeps the total momentum equal to 0, which is why we get recoil when guns fire, and how jet engines work, how rockets fly, and how balloons do their thing. Not that you're ever going to get to see all that at once, unless you go to a NASA-sponsored military-themed jet pilot birthday party. But you never know.
This is going to be all about sharing and forming bonds. That's right, it's all about non-metal atoms. Non-metal atoms share their electrons to form covalent bonds in a process that benefits from both. When two atoms share a pair of electrons, they get joined together. Depending on the atoms, this bond can use one pair of electrons or several pairs. The electrons that are shared are always in the highest occupied energy level of the atom. The sharing gives both atoms a complete highest energy level. The covalent bond that is formed is very strong. It takes a lot of energy to break it. Take hydrogen and chlorine, for example. If you know your atoms, then you know that hydrogen has 1 electron in its highest energy level and chlorine has 7. When these two form a covalent bond, this adds 1 electron to hydrogen's highest energy level and 1 to chlorine's highest energy level, completing both of them. Remember, 2 electrons fills the first energy level and 8 electrons fills levels 2 and 3. The combined molecule is called hydrogen chloride. The N of chlorine becomes a D in chloride, just to trip you up when you're doing your exam. Covalent bonding between two atoms needn't be with just 1 pair of electrons. You can get 2 and even 3 pairs, but always pairs. It's like socks, shoes, gloves or eyeballs. Here's a way to work out how many covalent bonds an atom can make. It's 8 minus, wait for it, minus the group number. Remember the periodic table? It gives the group number. What do you mean, what's the group number? If an atom is in group 7, then it's going to need 8 minus 7 equals 1 covalent bond. It's only got 1 gap in its highest energy level. Yeah, you get the idea. The number of vacancies in the highest energy level is the number of covalent bonds an atom can make. Oh, good magazine this. Might buy it. Ooh, special pull-out section as well. That's the stuff. Covalent bonds. There are 2 standard ways to draw these bonds. I like covalent bonds so much, I often draw them both. The most common is to join the chemical symbols with a straight line, like this. If there is more than 1 shared pair of electrons, then you need to join the atoms with more lines. A double bond uses 2 lines and a triple uses 3. You get the picture? Another way to show covalent bonds is a dot and cross diagram. Here is a chlorine atom. But when you draw a bonding diagram, you only need to show the electrons in the highest energy level. They're the only ones which can bond. Here's how you show a chlorine molecule. 1 pair of electrons is shared between the 2 atoms. Oh, it's a magical moment. Chlorine gas is made from molecules like this. And here's how you show oxygen gas. Notice that these 2 atoms share 2 pairs of electrons. This is a double bond. Oh yeah, let's mix it up a bit. Here are some compounds. That's when atoms of different elements join together. Isn't that hydrogen chloride, as a dot and cross diagram? And here is water. Notice that both hydrogen atoms now have 2 electrons in their highest energy levels, and the oxygen atom has 8. Okay, whatever you can smell, that's not me. That's ammonia. It's made from 1 nitrogen atom with 3 hydrogen atoms. And it stinks! There are 3 covalent bonds here. Carbon can make 4 covalent bonds. When it does this with 4 hydrogen atoms, you get, you've guessed it, methane. Methane, or CH4, is represented like this. Ooh, that was pretty exciting. Not the rocket thing, obviously. Just the fact that methane is formed with 4 bonds.
All animals and plants are made of cells, and cells need to give out and take in certain chemicals in order to function. Let's see how this happens. First, diffusion. Diffusion occurs when gas particles spread out. Diffusion also happens when particles dissolved in solution spread out. Here is a drop of ink. It has a high concentration of inkiness. When we drop ink into water, the inky particles spread out. They move from where there's a lot of ink, a high concentration, to where there is less, a low concentration. They move from a high to low concentration, so we say they diffuse down a concentration gradient. The greater the difference between the high and low levels, the faster the spread. When you burn toast, the smell gets round the house because of diffusion. Smoke particles move from the toaster, a high concentration of smoke, to the rest of the house, which generally you'd hope have a low concentration of smokiness. Well, I scraped most of the burnt bits off, and here's the toast going round my gut. Food gets turned into the chemical products of digestion, amino acids, sugars, etc. The concentration of these chemicals in the gut is high, but in the nearby blood capillaries it is low. They're desperate for digested toast. Result: the particles move from the gut to the blood by diffusion. Diffusion or wily cunning? No, right, diffusion. Take a deep breath in. Where does the oxygen in the air go? Well, firstly, into the alveolar airspace in the lungs. But where we need it is in the blood. You can breathe out now. How does the oxygen reach the blood circulating through the lungs? It diffuses from a high concentration of oxygen in the airspace across a thin membrane and into the blood, where there is a low concentration of oxygen. Without this mechanism, you wouldn't last the time it takes for me to explain all this. The thing to remember is that diffusion is movement from high to low concentration, and the greater the concentration gradient, the faster this takes place. Okay, I think you've sussed that. Let's look at the other mechanism for moving stuff around. That's called osmosis. For this, we're going to need a partially permeable membrane and two solutions with different concentrations. Before you dash off to get them, you've got loads already in every cell in your body. Each cell wall is a partially permeable membrane. Sounds attractive. But what is it? It's a barrier that lets some substances through, but not others. In osmosis, the chemical they let through is water. If we put pure water on one side of the membrane and a chemical solution on the other, then you know what's going to happen. The water will diffuse from high to low concentration of water. It goes from the pure water side, which is a high concentration of water, to the other side, where there is a lower concentration of water. This puts water into the chemical solution side, making it more dilute. Works every time. All the while, a small amount of water is flowing back the other way, due to random movement of molecules. But most movement is from pure water in the solution, making it weaker. Eventually, the concentrations on both sides of the membrane are the same. Then, there is an equal flow of water in both directions. We have reached equilibrium. Oh, that's better. Now, take a look at my sister's spider plant. Not looking too good, is it? If she'd remembered to water it, then it'd look like this. Water gets into plant root cells by osmosis, and then up into the rest of the plant by more osmosis. This makes the plant's tissues stiff, so they can hold up the leaves. So that's about it. Remember, diffusion takes particles from an area of high concentration to one of low concentration, as in the burnt toast incident. And osmosis takes water through a partially permeable membrane, from a weak solution of dissolved solute to a more concentrated solution, as in plant roots, so long as someone waters them in the first place, obviously. Your body is a temple. To be healthy, the body has to keep a huge number of things in perfect balance. Welcome to the world of homeostasis, which is all about staying the same, so as worlds go, it's quite predictable, ideally. Okay, so what needs to be balanced? Let's have some specifics. The key things are water content, iron content, body temperature and blood glucose concentration. Later, we'll look at what can happen when the body's regulatory functions go wrong, and what to do to put things right. But first, let's look at getting rid of waste. Unlike your bedroom or my house, the body cannot tolerate a build-up of waste. The concentration of waste products could affect chemical reactions and damage cells. So what things do we need to remove? Well, carbon dioxide for one. It's a waste product of respiration. That's the chemical reaction in cells that releases energy. Most carbon dioxide is carried to the lungs dissolved in the blood and leaves the body when we breathe out. Water is another thing we need to control. Water gets into your body through food and drink. Aerobic respiration in cells produces water too. Too much or too little water in our body cells will damage them. Although I think this fella's broken anyway. We all know what happens when we drink a lot. We dash off to the toilet. But the way to say this in the exam is, the kidneys respond to higher levels of water in the blood plasma by producing a larger volume of urine, which is also more dilute. Yes, the kidneys. Very important organs, those. What do? They filter out small molecules from the blood, water, salts, glucose and urea. They take everything out, but then they put some of it back. They put back all the glucose, and they reabsorb as much water and salt as is needed. That leaves urea, some water and some salt as waste, which is now called urine. Not because we don't like it, that's just its name. Urine is stored temporarily in the bladder, ready to make you panic when you're stuck on the bus. Dilute urine means the kidneys have got rid of a lot of excess water. Dark concentrated urine means the water level in the blood plasma is low, so that the kidneys have not filtered much of it out. Urine concentration changes depending on external temperature, exercise levels and the intake of fluids and salt. So now you know how to achieve exciting variations in urine colour. You also lose water when you breathe out and in your faeces. But there is another mechanism for removing water from the body. That most elegant of body functions. It is, of course, sweating. That's why we need to drink more on a hot day. Sweating has another function, cooling us down. The thermoregulatory centre in the brain controls our body temperature. This centre can detect the temperature of blood flowing through the brain and also receives impulses from temperature receptors in the skin, which help it keep body temperature at around a constant 37 degrees Celsius. Pretty impressive. But why bother? Temperature extremes are very dangerous. Really high temperatures can cause heat stroke and dehydration, and if untreated, even death. At other extreme, very cold temperatures can cause hypothermia, which can also lead to death if not treated. It's just death everywhere you look! Death! When your body gets very cold, it's your hands and feet that feel it first. That's because the body works to maintain its core temperature. Ooh, I better change the subject, I'm freezing. The body's cells need a constant supply of energy. This comes from glucose carried around the body dissolved in blood plasma. Blood glucose concentration is very important and it must be kept within narrow limits, not too high, not too low, round about there. The pancreas monitors glucose levels and controls them by producing a hormone called insulin. Insulin causes glucose to move from the blood into the cells. When blood glucose is too high, more insulin is released. This means more glucose moves into cells, reducing the blood glucose level. When blood glucose is too low, less insulin is released. Less glucose moves into the cells, more stays in the blood. This raises the blood glucose level. Simple but effective, unless you're diabetic. People who suffer from diabetes cannot control their blood glucose level. This is a very dangerous situation and can be fatal. Diabetes comes in two variations, called surprisingly type 1 and type 2. In type 1, the body does not produce enough insulin. Diabetics must pay careful attention to the diet and must regularly inject themselves with insulin. Type 2 is often the result of a poor diet and obesity. It is usually controlled by diet and exercise, which is also how you avoid it in the first place. The irony. So, to recap, water balance, body temperature, salt and glucose levels are all critical to life. Homeostasis means controlling these to maintain a constant internal environment.
Ever wondered why you look like your parents? Well, not as old, obviously, but still similar. It's all in the DNA. In the next few minutes, we're going to look at cell division, using this amazing mechanism you've developed from a combination of your mum and dad's gametes. Here is a typical cell. This is the nucleus. Zooming in, we can see the chromosomes, and the chromosomes are made from long molecules of DNA. Watch CSI, The Bill, Silent Witness, and they are always looking for DNA. So why is it so important? Because each person has unique DNA. Unless you are an identical twin, in which case you and your twin share the same DNA. So you better hope they're not a serial killer. So what is DNA? It's a large complex molecule that carries the genetic code that determines just about everything about you. Hair colour, eye colour, hatred of broccoli, maybe, maybe not. DNA is shaped like a double helix, like a ladder that's been twisted into a spiral. A very small ladder. Short sections of DNA are called genes. Each gene has a specific purpose. It has the instructions for making a particular amino acid. These join in a particular order, again controlled by the genes to form proteins. So genes control proteins, which is how living things are made. Let's just go over that again. Inside each cell nucleus are chromosomes that are made from DNA. DNA contains genes. Each gene has a code to make a protein. The protein is made out of amino acids that are joined together in the order determined by the code. The proteins go on to make living things that go on to live happily ever after. Oh. No, wait. But how do these living things grow from single cells? When living things grow or repair damage, they need to make new cells. How do they do this? Answer: mitosis. A cell can divide into two. These two new cells are identical to the original one. They have the same DNA. It's a 5-step program. First, we take a parent cell. Step 2, the chromosomes in its nucleus make identical copies of themselves. Step 3, the chromosomes line up in the centre. Step 4, the copies separate and move apart. And step 5, the cell splits into two, forming what we call two daughter cells. Each one has a copy of the original parent cell DNA. So this cell has two new daughters, except there's not really a parent cell anymore. The process can repeat, each new cell dividing into two. Cells can multiply this way, creating identical copies every time. This is how living organisms grow or replace damaged cells. Cloning. It's been around for longer than you think. Plants, microorganisms, and even some animals can reproduce just by making copies of themselves in this way. Feels like cheating. No awkward first dates, no hairdos, no fashionable trousers. It's asexual reproduction. As no new DNA has been introduced, the offspring are genetically identical to the parents. Now, what if you want offspring that are not identical to the parents? That would be useful. Variation, adaptability, survival of the species, new species, evolution, and, let's face it, the thrill of the chase. Well, we need to know a bit more about chromosomes. They generally come in pairs. You have 23 pairs of chromosomes in the nucleus of each cell of your body. Quite a squeeze. The fact that chromosomes come in pairs plays a big part in the other type of cell division, meiosis. This is part of sexual reproduction. Meiosis only happens in the reproductive organs and produces special cells called gametes, eggs and sperm. Meiosis ends in the pairs of chromosomes getting split. The result is that egg and sperm cells have only 23 single chromosomes. Not the usual 23 pairs. That's half the genetic information needed to create a new person, animal or plant. Coincidence? No. Fertilization happens when the male and female gametes join together. Their 23 single chromosomes pair up to give the full 23 pairs. So this newly formed cell contains a unique mix of chromosomes from each parent. Sexual reproduction in this way introduces variation into the genetic code. The particular mix of the two sets of DNA is unique. So, how does meiosis work? Back to the reproductive organs. The 23 chromosome pairs start by copying themselves and double up. Then sections of DNA get swapped between similar chromosome pairs. The swapping of DNA is where the genetic variation comes from. Then the cell divides into two, 23 pairs into each half. These two cells divide again, and this time the chromosome pairs are split up. So the 4 cells we're left with have only 23 single chromosomes. So there we have it, the finished product, the gametes, sperm cells and egg cells, looking for a mate. Do you want fast biological reactions? Well, yes you do, to keep alive, and it's enzymes that get things done. They make chemical reactions happen, but they don't get used up. Enzymes help large molecules join together or come apart in just the right way. So how does the trick work? Enzymes are proteins, large molecules formed from long chains of amino acids. They are folded into complex 3-dimensional shapes. Smaller molecules can fit into the shapes of the enzyme, like a 3D jigsaw. But less boring. That's how the enzyme does its job. The enzyme positions the smaller molecules, called substrate molecules, so they can be joined in the right places. Go on, substrates, get in there! And get out again. The product molecule has to separate off from the enzyme. The enzyme is free to carry on joining more and more substrate molecules. They can only do one job, and they do it over and over again. No imagination. Some enzymes do the opposite job. They split large molecules into smaller parts. In a very specific way, of course. Only molecules with the right shape fit. It's called the lock and key model. Just like only the right shaped key fits into a lock. Here's a technical term. The place on the enzyme where the substrate molecules fit is called the active site. The shape of the enzyme is critical. Change its shape and the substrate molecules won't fit the active site. The enzyme stops working. If this happens, we say the enzyme has been denatured. How does it happen? Enzymes can be denatured by high temperatures or extremes of pH. Whichever it is, don't say the enzyme has been killed. Enzymes are proteins. They're just large molecules and not living things. Here is a graph. Higher temperatures increase the frequency and energy of collisions between the enzyme and other molecules. So the rate of reaction increases as temperature increases, up until about body temperature. That's ideal for most enzymes. Your body has loads of jobs that it needs enzymes to do. So far, so good. But if the temperature continues to rise, then the enzyme starts to get denatured. So it doesn't work as well, and the rate of activity falls. You can see that an enzyme works best at a specific constant temperature, body temperature. The wrong pH can also denature an enzyme. So here's another graph. For this enzyme, activity peaks at pH 8 and then falls away either side of this. Different enzymes work best at different pH values. For example, the stomach is very acidic, so enzymes there work best at pH 2 to suit the environment. You can probably imagine what their graphs look like, but we're going to draw it anyway. Enzymes take part in many different cell processes, like photosynthesis in plants and joining amino acids together to make proteins. They're also involved in aerobic respiration. Now let's get this straight. Respiration is not the same as breathing. Respiration is the chemical reaction that releases energy from glucose. There are enzymes that catalyse this reaction. Most of the work takes place inside cells, in the cytoplasm, in tiny objects called mitochondria. The energy is used for contracting muscles, joining molecules to form proteins, and lots of other things, including maintaining body temperature in birds and mammals. Microorganisms produce enzymes and some release them out into the surroundings. We can collect these and make them into useful chemicals for the home and industry. Oh, thanks. Take a look in the cupboard at all those biological detergents. Why are they called biological? Because they contain enzymes that digest proteins and fats to make water-soluble products. This helps to get the stains out. So there you are. Enzymes are biological catalysts. Without them, you'd have no super clean clothes. Oh, and you'd die, because chemical reactions in your body wouldn't happen. What happens next? Yep. Enzymes catalyse digestive reactions to break down the natural polymers found in food. Right. I think we better just get on with it. In digestion, large molecules from food are broken down into smaller, soluble ones. These are absorbed into the blood plasma and lymph and transported to where the body can use them. We'll look at how starch, proteins and fats get digested. And hopefully, I get to eat this steak and chips. Enzymes are biological catalysts. But you knew that. Digestion relies on them, and it happens in the gut, which is good. Better than on the plate. So, the gut then. Here is your digestive system. Looks nice, doesn't it? The long tubes are the gut, where digestive enzymes act as catalysts in the breakdown of food molecules. These digestive enzymes are produced by specialised cells in glands and the lining of the gut. But unlike other enzymes, digestive enzymes work outside of the cells that produce them. They pass out into the gut and start to work on your chocolate biscuit. In fact, they can get to work on anything. Is that all you need to know about digestion? Oh, if only. Then we could spend the rest of the time relaxing. But you also need to know which enzymes are needed for what jobs. Different parts of the gut produce different enzymes. Amylase is produced in the salivary gland, pancreas and the small intestine. Amylase is a type of carbohydrate. It catalyses the chemical reaction that breaks down starch into sugars. Protease is produced in the stomach, pancreas and the small intestine. Protease breaks down proteins into amino acids. And lastly, lipase. Lipase is produced in the pancreas and small intestine. Lipase breaks down lipids, oils and fats, into fatty acids and glycerol. Amylase, protease and lipase. Only 3 to remember. All 3 enzymes are produced in the pancreas and small intestine. And then, in addition, amylase is produced in the salivary glands and protease is produced in the stomach. Different enzymes work best at different pH values. The stomach produces hydrochloric acid to begin digestion and to kill harmful microorganisms too. The stomach is a very acidic environment. So it's no surprise that enzymes in the stomach work best at low pH values. Food travels from the stomach into the small intestine where it's all change, because the enzymes here work best in alkaline conditions. That's pH values above 7. A substance called bile makes this change. Ugh, sounds delightful. Bile is made in the liver and stored in the gallbladder. It's released into the small intestine to neutralise the stomach acid. This creates the alkaline conditions the enzymes need to carry on digesting the food. So by the time we get to the small intestine, everything is being digested. The enzymes from the pancreas mix with those made in the small intestine. It's all going on, a gloopy goo of digestion. Amylase, protease and lipase digesting carbohydrates, proteins and fats to produce glucose, amino acids, fatty acids and glycerol. These diffuse through the lining of the gut and get into our blood. They're all useful chemicals. Everything the body needs.